So in our energy balance, we have two unknowns but only one equation. And so that tells us we need to go to another equation in order to solve for all of the unknowns. And so naturally, our next equation that we should look at is the entropy balance. Okay? Since we're dealing with an open system, we're going to use the entropy balance for an open system. So ds dt is going to be equal to the entropy carried into or out of the system by the various streams. So I'll write it like this. Plus any sort of heat terms divided by the temperature associated with those heat terms, and then Sgen. Based on the assumptions in our problem, we're assuming it's adiabatic, so there are actually not going to be any heat terms. And we're also assuming it's reversible. Specifically, the compressor is reversible. So we're not going to be dealing with any Sgen terms. And because we're treating the system as steady state, that also means the entropy won't be a function of time. And so our entropy balance is going to simplify down to this. And from our material balance, we know that M2, mass flow rate, is equal to M1. And because this is equal to 0, we can actually cancel out both of these things. And so what we get is that the entropy going into the system is equal to the entropy going out. Here I'm writing it in terms of the specific entropies, but equivalently, we could also write it in terms of the molar entropies. Right? And so here we find that the entropy going into the system is equal to the entropy going out of the system, equal in magnitude. And typically you see this when you're dealing with adiabatic and reversible systems, right? And so adiabatic, that makes the Q term 0, and reversible, that makes Sgen 0. Right? And as a result, your change in entropy is also going to be equal to 0. Okay? And so, ultimately what we want to do with this sort of relationship is we want to use it to figure out, one of our unknowns in our energy balance, either Ws or T2. And so really what we're going to do from this entropy balance is we're going to use it to get information about the temperature of the outlet stream from the compressor, right? And so to do that, we need to relate these entropies to temperature. And so the way we're going to do that, or in other words, to calculate our molar entropies, so our SIs, what we could do is we could use the same shortcut that we used when we were dealing with closed systems. Specifically, we could use the fundamental entropy equation. Okay? So here, from our fundamental entropy equation, we have this. And we know if we're dealing with an ideal gas, we could simplify the equation to this. So now it's Cp over dt over T minus R dP over P. Okay? And so what we could do here to develop a relationship between temperature and pressure, we just had to integrate this equation. So for instance, S2, we would integrate from Tref to T2, this equation, or this term, and then for the second term, we would integrate from our reference pressure to P2. Okay. The gas constant is a constant, so we could pull that out of the integral. Okay. And so for S2, after we integrate, we get this. So we have natural log terms for both temperature and pressure. And we know our reference temperature and pressures are just equal to that inlet temperature and pressure. So S2 simplifies into this. Similarly, we could do the same thing for S1. So if we go through the integration and plugging in the reference conditions, we get this. T1 minus R P1 over P1. Right. And this is fortuitous because the natural log of T1 over T1 is the natural log of 1, which we know is 0. And the same thing here. And so we find that our entropy, S1, which is at the reference conditions, is exactly equal to 0. Right? So I want to highlight that here. Entropy is 0 at the reference conditions. Okay? All right, in any case, if we take S2 minus S1, we get that it's equal to this. And we know from our entropy balance that S2 minus S1 is exactly equal to 0. And so in our statement, we know everything except for T2. Right? And so now, unlike the energy balance where we had 2 equations and 2 unknowns, now we only have 1 equation and 1 unknown. So this allows us to solve for that T2, which is about 189 degrees Celsius. Right? And so by using the entropy balance, we had an additional equation for calculating our unknowns. Now that we have T2, we could go back to the energy balance and we could plug in. Celsius minus 20 degrees Celsius. We get that's about 400 or 4.95 e to the 3 joules per second. Or another way to say it is it's about 4.95 kilowatts of shaft work that's needed in order to compress this air. Okay. All right, so part A, we wanted to figure out the temperature and shaft work associated with the compressor. For part B, now we just need to figure out the heat that's associated with the heater. And so at this point, we just need to do balances around the heater. For the heater, the material balance is basically the same, such that we get that the molar flow rate coming out of the heater is the same as the other molar flow rates. Okay. With our energy balance, we'll once again start with the open system energy balance. Right? And then if we account for the enthalpy going in and the enthalpy going out, Steady state, so the left-hand side is all 0. Just a heater, so there's no shaft work. Okay? And we know that N2 is equal to N3. So if we rearrange our equation, we get that Q dot for the heater is equal to N2 times H3 minus H2. And if we apply the heat capacity definition, we get that N2 is equal to this. T refs cancel. Okay, so that we get this. On the right-hand side, we know everything, so that makes calculating Q dot fairly straightforward. For mole K, 400, that's 189. So that means we need to put in about 6.19 e to the 3 joules per second, or 6.19 kilowatts, into our heater in order to get the temperature up to 400 degrees Celsius. Okay? And so in this problem, it was a demonstration of how to use the open system energy balance in order to solve a basic thermodynamics problem. And really the key thing that I want to point out here is in order to get the entropies, the molar entropies of the streams going in and out, this is where we turn to the fundamental entropy equation.